All right, we're taking a look at the exponential function, and we're going to get an idea of its basic shape and how to graph it. Now, when we talked about this function, we said it was f of x equals a b to the x. Well, we're going to take a off of there because a would actually be a stretch if you think back to our section on transformations. So the basic shape here is just this, fx equals b to the x. So we've said when we talked about this basic function that the values for b have to be greater than 0. So what we said is 1 can't be 1 either because 1 has no growth at all. So this is a function that talks about either growth or decay. So if we're above 1, we're growing. If we're between 0 and 1, we're decaying. So negative values, so 0 doesn't make sense because you'd just be exponentially multiplying by 0. That doesn't mean anything at all. And if you think about what would happen with negative values, suppose this was something like negative 2, and then when you squared it, it would be a positive value. If you cubed it, it would be a negative again. So this function applies to values of b that are greater than 0. That's what it's all about. So either the growth or the decay. Now, some other important features. We always have a horizontal asymptote where y equals 0. So if you remember, a horizontal asymptote is just it's a line that can't be crossed. So we will never cross the line y equals 0. Now, the reason is, how are we going to turn a positive value of b? How is some exponent going to turn this into a negative number? It can't. We have a positive b, even with negative exponents. So if suppose it was 2, if I had a negative 4 as an exponent, that just means 1 over 2 to the 4th. It's going to get me a very small number, but there's no way I'm going to make negatives. So my values of y are limited by this asymptote. We can't go below the line y equals 0. Now, if you think real quickly about the domain, all value, we're going to get infinitely close to this line y equals 0. But so if we had our ruler going up the x-axis, we're hitting something everywhere. Even with this arrow on the other end, we'd be hitting everywhere. So my domain is negative infinity to infinity. Now my range are my y values, and we just said we can't get 0. So if I were using my ruler, just above 0, I would start hitting something, and I would go up the line and go on to infinity. Now, let's talk about, we're going to graph it. Okay, I think I should show this on the next screen, or this one. Yeah, let's go back here for just a second. So there are two very important points that we need if we're going to graph this function. I would be happy with just these 2 points. You could pick a third to try to graph it. But this is the shape of growth. This is the shape of decay. Now, look at the 2 key points. Anytime, no matter what b is, anytime b is taken to the 0 power, anything to the 0 power is always going to be 1. So if you don't have an a on here, the point, the point 0, 1 is always going to be on the graph. Every time, right there. Every single time, unless there's an a, this is going to be the y-intercept at 1. It has to be because putting 0 in for x always gives us 1. Now look at this other point that's always going to be on there. What would happen if you put b and you give it an x value of 1? It's always going to be b every time. So these 2 points are always on the graph, 0, 1 and 1b, and you can use those to make a sketch of the graph. So that's what they're asking us to do here. I have 0.25x. So to the x power, I've got an exponential with a base of 0.25. Now they've created some points here, but I wouldn't really need you to do that. What I would want you to see, this would be enough for me. So you put in 0 for x, you always get 1 every time. You put 1 in for x, you always get b every single time. So I would graph those 2. We know it's decay because we're less than 1. So of course we're decaying. And so it would be good enough for me if you just drew that swoop and just made sure you went through those 2 points. It's fine if you wanted to plug in another. They put in -1 and found out it gets 4. But it wouldn't be necessary for me. I would just be asking that you went through those 2 points. I want you to understand those 2 points are on the graph. And I'd want you to know that it's decay here instead of growth. Now, let's talk about the domain and the range. If this is my graph, and I had my ruler coming up the x-axis, do you see the domain? Well, they've got it down here. The domain is going to be negative infinity to infinity. This is always going to be true on an exponential function. It's always going to be negative infinity to infinity. And the same for the range. So remember, there's that asymptote here at y equals 0 that it doesn't cross. So my range is going to be 0 to infinity. So if I take my ruler up the y-axis, I'd start hitting something just above 0, and I'd continue hitting it all the way up. Okay, let's see. Now let's do one of our own here. So first thing I see here, with a b of 4, this is growth. Okay. Now let's put on our key points. If I put in 0 for x, I get 1 every single time, because anything to the 0th power is 1. So there's my first point. If I put in 4, or I'm sorry, if I put in 1 for x, I'm going to get 4. Every time you're going to just get b. So if I put 1 in here, I get b. So put in 1 for x, 1, 2, 3, I get 4. Sorry, dots are an issue for this. Okay. Now this is exponential growth, so it would be sufficient for me if you just drew this. If you want to, you can add one more point. Suppose you could put in 2, and you'd get 16. So yeah, I guess I wasn't quite steep enough. If you put in 2, you'd get 16, so you'd be way up here. So it should have been steeper. So 4 is quite a bit of growth there. So okay, but that's the idea. Now let's talk about the domain and the range. So well, the asymptote is easy. It's always y equals 0 for this, unless we shift it around, which we'll see in just a minute. Now the domain for an exponential is always the same. It's going to be negative infinity to infinity. The ruler would hit everywhere as we came up the x-axis. And the range, unless we transform it, move it around, it's going to be the same. We're going to start, we don't want 0, but we'd hit something going up all the way, the rest of the way. Okay, now let's take a look at some transformations here. Now this is going to follow all the rules that we saw previously, except it looks a little strange because now it's happening up high up here. But it's still the same principle. It's still happening up here on the x. So if you add 1 to x, what we saw is that moves us to the left 1. So we're going to take this initial graph and we're going to move it back 1. Here. I don't know if you'd really need the precise shape here, but we'll put it on here. So remember, if you put in 0, you always get 1. If you put in 1, you always get b. So this is the function that we're transforming, this guy. Now we're going to move him 1 to the left and then down 3 because of that. So take this initial graph of 2 to the x, and we're going to move it back to the left 1 and down 3. Now, it's the same graph here. It's a little weird to see if you wanted to plug in some test points here, but we're going to be moving this spot right here back 1 and down 3. So back 1 would make it at -1, down 3 would be at -1, -2. Hold on, down 3, 1, 2, 3, yeah. -1, -2. Now this point, if you wanted to mark one more, we were at 1, 1. So we move him back 1 and down 3. We would now be at, hold on, I'm doing that wrong. 1. Now we're going 1, 2, 3. So yeah, we'd be at 0, -1. Okay, so they've got one more point marked that I didn't mark, but this is the idea. We went back 1, down 3. Now, how about our asymptote? Well, our asymptote had been along this line here at y equals 0, but we've moved the entire graph down 3, so that horizontal asymptote went for the ride. So my horizontal asymptote went down with it. So it was at 0, now it's at 3. And how about the domain? Well, the domain has not changed. We did move this back and down, but my ruler would still hit something everywhere. So my domain is still negative infinity to infinity. Now, how about my range? My range is going to take my ruler, because we shifted down, it's normally 0 to infinity, but because we moved down, we're now going to be -3 to infinity. So all of this just changed because of the shift. Okay, so I'm going to do this again. So 0, 1 is always on that if there's no a. So we're doing the original function 2 to the x, and then we're going to shift it again. So if I put in 1, I would get out 2. And so here's my original function. Now we are moving it to the right 1. Do you remember a minus moves us to the right? So we're going to go right 1 and actually up 3. So I'm going to go right 1 with this point, up 3. And then my second point was at 1, 2. So my second point was here. I'm going to move him 1 to the right and up 1, 2, 3. And he'll now be there. So again, those two are sufficient for me, but you could have made a third point and you would have shifted that too. Move the point 1 to the right, 3 up. Okay, well let's start with the asymptote. So it was y equals 0 up here, but we have shifted this whole graph up 3. So now the asymptote is at y equals 3. That's the line it would not cross. Now how about the domain? The ruler is still going to hit everything. So my domain is still going to be negative infinity to infinity. How about my range? So this way with the domain. With my range, we've moved everything up. So it was 0 to infinity. Well, now it'll be 3 to infinity. Okay, this is not a bad question. I was looking at this before I started here. It's clever. I would never, ever test you on a question like this, but what they're trying to get you to see is that suppose graphically we wanted to solve an equation. What you could do, and they're giving you the calculator steps here, you're just going to put, if you have a TI-84, you're putting this in as an equation, a y equals, you're going to select it as y1, and you would put this in. So you're taking the right side and you're putting it into your calculator. Now, if you then made a line that said y in y2 that says 42, it's going to make a y line. So if you had your graph here, it's going to make a y line at 42, where y is always 42. Does that make sense? Well, if that's the case, if you have this exponential function, and you have the line 42, which that's this point where they intersect, would be the solution. Does that make sense? So this would just be the exponential function if you graph this on the right. If you add the horizontal line, y equals 42, you're saying, okay, well, when is this 42? Well, you could find that y value and find the point right there where they intersect. So whatever the x value is where those two intersect, that would be the solution. And so again, they're giving the calculator commands. I'm not going to take you through that. I would not ask this question, but it's interesting to note that that's a clever way that you could do it. So if you did that, you'd get approximately 2.16. Okay, let me just see. So one more time, I'm not going to work this. I don't know the answer on this. I'm not going to do this graphically. But you would put this in your calculator for y1. So put that in for y1. Put this for y2. And just get yourself a sufficient window so you can see where the two intersect. And the value of y at that point of intersection is another clever way to find the solution without having to do any mathematics. I mean, you could do this mathematically as well with something called a logarithm, which I think is coming up in the next chapter or so. But if you wanted to do it graphically, that would be a clever way to do it. Okay, so we're looking at that exponential. Just remember, the two key points that you need is if you put 0 in for x, you're always going to get 1 out of an exponential every time. If you put 1 in for x, you're always going to get the value of b. And all of our transformation rules from our previous section still apply. The right and left transformation are happening up in that exponent, but it's still the same thing. And that would then, if you have any shifts to the range, if you move it up or down, that's going to make some changes to that asymptote and also to the range.